Picture an astronaut on the moon, bounding across the surface in leaps that would be impossible on Earth. She hasn't lost an ounce of flesh, hasn't shed a single atom. So what actually changed to let her jump so high? Something about her physical situation has shifted, even though the amount of matter making up her body is exactly the same as it was on the launch pad. That puzzle is the key to understanding two words people use interchangeably every day, but which physics keeps firmly apart: mass and weight. You already know from ordinary life that kilograms belong with mass and newtons belong with force. You buy a kilogram of apples, and you might describe a punch as landing with a certain number of newtons. Even though everyday speech often blurs mass and weight together, saying, "How much do you weigh?" when we really mean mass, the units themselves are already sorting these ideas into two separate boxes for you, ready to be defined properly. Consider two instruments you might have seen in a lab. A beam balance has a pan on each side, and you slide reference masses until the beam sits level. It's directly comparing how much matter is in the object against how much matter is in the known masses. A spring balance, by contrast, has a hook and a spring that stretches. The more the spring stretches, the greater the pulling force acting on whatever hangs from it. Here's a prediction to make before I explain anything further. Imagine you take both instruments, along with the same 1 kilogram block, to the moon, where gravity pulls far more weakly than it does here. What would each instrument show? The spring balance reading falls because the gravitational pull on the block is smaller. The beam balance reading stays exactly the same because it's comparing matter against matter, and the block still contains the same amount of matter it always did. That prediction only makes sense once mass is defined precisely. Mass is a measure of the quantity of matter contained in an object, measured while that object is at rest relative to whoever is observing it. It doesn't care where the object is, orbiting a planet, sitting in a lab, or drifting between stars. The matter itself doesn't disappear or multiply just because the surroundings change. Weight is a completely different kind of quantity. It's a gravitational force, the pull that acts on an object because that object has mass. Because weight is a force, it's measured in newtons. And because a force depends on the environment producing it, weight can be different in different places, even while the object's mass, its quantity of matter, refuses to budge. Here's a deeper way to picture why that pull exists at all, which goes a little beyond the core idea. Every mass sits inside a gravitational field, a region of space where another mass, like a planet, reaches out and pulls on anything nearby. Weight isn't some separate property stored inside the object. It's the effect of that surrounding field acting on the object's mass. Change the field, and you change the weight, without touching the mass at all. Picture a diagram of a planet with arrows drawn pointing inward toward its surface, spaced closer together near the ground and farther apart with distance. Those arrows represent gravitational field strength at each location. And the key idea to read from the diagram is that the length and direction of an arrow tells you the force acting on each single kilogram of mass placed at that point, not the total force on any particular object. That idea of force per kilogram has a precise equation attached to it. G equals W divided by M. Before using it, fix what each letter means. G is the gravitational field strength, measured in newtons per kilogram. W is the weight, the gravitational force in newtons. And m is the mass, in kilograms. Read the equation as a sentence. Field strength tells you how many newtons of pull act on every kilogram of matter at that location. There's a second, equally valid way to read that same symbol, g. Instead of thinking force per kilogram, think acceleration of freefall, the rate at which an object speeds up as it drops, with no other forces acting on it. Both readings describe the identical physical quantity. A strong gravitational field pulls harder on every kilogram, and it also makes objects accelerate downward faster when they fall freely. Try a concrete case. Suppose a lab crate has a mass of 5 kilograms, sitting somewhere with a gravitational field strength of 10 newtons per kilogram. What's its weight? Using W equals m times g, 5 kilograms multiplied by 10 newtons per kilogram gives 50 newtons. Notice how the units check out too. Kilograms cancel with the per kilogram, leaving you with newtons, exactly what a weight should be measured in. Now, flip the problem around. Suppose a probe with a mass of 20 kilograms lands on a distant moon, and instruments there measure its weight as 32 newtons. What's the gravitational field strength of that moon? Rearranging G equals W over m, you divide 32 newtons by 20 kilograms, giving 1.6 newtons per kilogram, a field far weaker than Earth's, which is exactly what you'd expect on a small, low-gravity world. Here's where the tempting wrong idea creeps back in. Thinking an object simply weighs less on the moon because it somehow contains less stuff there. Test that against the equation. The crate's mass stays 5 kilograms wherever it goes. The matter hasn't changed. But if the moon's gravitational field strength is roughly 1.6 newtons per kilogram instead of 10, its weight becomes 5 times 1.6, which is 8 newtons, not 50. The mass never moved, only g changed, and weight changed because g changed. This is exactly why a balance is such a trustworthy practical tool. Whether you're using a beam balance to directly compare mass against mass, or comparing readings from calibrated spring balances to compare weights, the technique lets you check one object against known standards. A beam balance, because it compares matter against matter, gives the same result no matter where the gravitational field strength happens to be, which is precisely why it stayed steady in your earlier moon prediction. Quick check before moving on. 2 quantities. One is 490 newtons, the other is 50 kilograms, both describing the same object on Earth. Which one is the weight, and which one is the mass? The 490 newtons is the weight, because it's measured in newtons, the unit of force, and it's the value that would change if you moved the object elsewhere. The 50 kilograms is the mass, the fixed amount of matter, unaffected by location. Pull it all together. Mass is the invariant quantity of matter an object contains. Weight is the gravitational force that a field exerts on that matter, and the two are linked precisely by weight equals mass times gravitational field strength. That relationship holds anywhere in the universe you care to test it, on a planet, a moon, or in deep space, because it isn't describing a special property of Earth, but a general rule connecting matter, force, and field. Next time you meet an unfamiliar world with its own gravitational field strength, you now have the compact rule to work out how heavy anything would feel there. using nothing but its mass.